transfer learning deprecates XGBoost. I've always been a great defendant and great advocate. Not advocate, but I use it myself, and most of the times XGBoost. And when I say XGBoost, I mean CatBoost or LightGBM or any of these kind of tree-based model on extreme gradient descent. I've always used them as the and defend them as the as the main tool and as the main framework for doing for doing machine learning, especially in tabular data where it is obvious that there's the the main application of them. Um, Much more in favor of linear models for being more simple or unexplainable or whatever we want to use them, which I stopped using them as a first option quite a time ago. But it's the topic is more discussed about using XGBoost like models or deep learning frameworks or deep learning architectures. It's very I don't know what Boyan Tunguts would say about me talking about this. Probably he will get very pissed off about doing anything else, any other thing different from XGBoost, which for many applications, for many reasons, for a long time ago, it's been probably the best choice that you can do for machine learning in terms of efficiency and prediction accuracy, uh, happiness to use them because of little assumptions come from them, little feature engineering is required. They simply just work and work very well, and they're even very efficient. It, but I've been doing this travel myself, trying to leave, not trying, but maybe forced to leave them behind for many reasons. But there is a core reason for leaving them behind in favor of deep learning. Deep, and I can say it just straight ahead as we said it, as I saw at the beginning. XGBoost like models do not enable you to move into frameworks of transfer learning or pretraining fine-tuning schemas, which I think is the main is the main benefit of moving into neural network architectures and deep learning with all of the problems that it takes with it in terms of assumption of data, mm, ability to well, they sometimes they do not work out of the box because you need to iterate a lot of architecture because architecture for neural network if we use native TensorFlow or PyTorch, it's just too flexible to say where should I start with. But what nobody explains better and demonstrates better and never, as far as I know, did it before than Jeremy Howard about transfer learning with the ULM fit. This is the neural network that Jeremy Howard used in order to. Well, there was a big war and a great dominance for NLP models, and the war was totally dominated by, let's say, by Google back in mid 2010s and 2015, so on. Google simply tried to drag the war into a battle of scale, a battle of computing resources, with the TPU, with the tensor processing unit, and with the data advantage that they definitely had at that time. So they try to build this story about deep learning. It's all about putting together massive amounts of compute and data together. Obviously, they try to drag the world into this open field in order to they to leverage their advantage in those in those main areas. And then Jeremy Howard came and kicked their ass off with a couple of notebooks. And the core idea of him doing that was because he was able to do, and he was the first proponent and first believer and take to the and get committed to transfer learning. He basically tried to build a moderately, not so sophisticated neural network, not that big, not that many parameters, and simply taught him to read by touching English by reading the whole Wikipedia several times. Once that he was able to, the model was able to read and to learn English and to manage basic concepts with this pretraining task, it was just a handful of instances, a few iterations to fine tuning to the specific task that they wanted to use the model in. And it was so efficient and so performant that it simply went to the top of the leaderboard with yes, a handful of people, a few resources. With this just a smart idea of moving into a two-tier system with pre-training and fine-tuning. What we have since then, well, the full revolution with LLMs is just based on that. It's just based on pre-training schemas, providing models with massive iterations on basically the whole internet, teaching them to create and to predict the next token without any specific objective, in a purely unsupervised manner. So afterwards, any kind of hard problem is just a few short learning problem, because the base model, the foundational model is so strong. It contains and compresses so much knowledge that any further task is just a matter of basically correcting and fine-tuning towards a specific objective. The same way our brains learn so quickly because, well, the base neurons are contain so much latent knowledge that anything new for them is just reading a couple of paragraphs and suddenly you understand it all. And XGBoost does not provide you with that. So we get a massive revolution in this. Even for some time now, XGBoost has shown state of the art. We can use once more that term, but it's simply beaten many of the neural network architectures in tabular data, because tabular data, well, for image, for sequences of text, unless you create it, we can call that unstructured learning because there are no features into that. It's just simply massive data, sequences of tokens, or matrices of pixels in the case of images. You cannot feed that directly into XGBoost, or in order to transform it into tabular data, you need to fall into assumptions about what feature engineering is better for that particular case, which doesn't scale. So simply deep learning works better for non-tabular data because those are too hard to try to become tabular and be able to be treated as XGBoost models. So for some time, if the base is tabular data, XGBoost was performing better. But we have now this transfer learning schema. One of the mental models that we can take for that is try to come up with unsupervised embeddings for tabular data, which for many times we come in these schemas. We have some, for instance, if we got descriptions, text-based features for within a tabular data set, it becomes very natural to perform some unsupervised embeddings using text-based models for deep learning and turn the text description into sequence of tokens, and once there, after that, simply perform an unsupervised embedding. So we can do unsupervised learning for these tabular models for text data very naturally. But recently we have tools and frameworks and techniques which allows us to apply this to generate these unsupervised embeddings with tabular data itself. Well, it's not new that we had for a long time ago principal component analysis for numerical data to project it, but it is a linear transformation and it doesn't capture very subtle patterns where it is restricted to linear relationships between the features. So it is always limited. For many times we had autoencoders, which is unsupervised learning, and it's fitted both for text and numerical data, and we can always generate unsupervised embeddings for the raw data set and then train an XGBoost on top of that in a supervised manner. But the idea of putting attention mechanism into tabular data is so powerful, because one of the things that enable the explosion of the large language models and the ability to do deep and the explosion of deep learning is specifically that attention is all you need. The attention mechanism. It's so strong because what it does is somehow puts into deep learning the key feature, the key strength of XGBoost, which is this ability to map and learn the interactions between features. For attention, we'll use for text-based models. For deep learning attention in text-based models, we assume that we are predicting the next token. We are assuming a sequence type of data as input, and so attention allows you to learn the interrelations between tokens at several places, several positions within the sequence, within the input sequence. So that doesn't come naturally into tabular data because we move from sequence to tabular, but I've I've used this tokenization very frequently in the past before doing that, but now it comes more natural than ever to try to move tabular data into tokens. So we can generate and order sequences, tokens, out of the features of the of the features of the data. So tabular data, I mean. So you concatenate um, the columns and the values for the columns, and you create a sequence. And you can simply take the attention mechanism at its core, and you can get rid of the positional encodings. So you are not modeling anymore an order sequence, but an order set of things together in a two-way matrix. Um, so now we have the attention mechanism learning the interdependencies between and the crossing between features in a tabular data set, which should be the key advantage and the reason why XGBoost and tree-based model beat everyone else. But now uh, it's not the only one in the town having that, because attention can do it as well for tabular data sets. And it's so powerful because of a few reasons. First of all, um, it is able to capture this by having this, uh, learn these interactions between features in a two-way matrix by using the attention mechanism. It is able to capture less implicit interactions between features than those that tree-based models are able to track. So it has basically a two-way matrix of the feature of the features together, and you can do some very you can project it into more robust latent spaces and learn their interrelations between the features in this projected space, which is much more powerful. It's much more expressive and can handle with greater orders of abstraction than the simply brute force combination of tree splits by the tree-based models can handle. So they're much more explicit. It is true that tree-based models capture very well these long-tail skewed distributions for numerical features because tree-based models simply focus on the ordering and tries to set threshold a split. Um, so it's very robust about these irregularities, about this skewness, about these non-normal distributions of data. But what happens is that proper scaling and with a powerful enough neural network and attention mechanisms big enough, and it probably it's starting to become less a bottleneck, and attention mechanism has a better, more profound way of learning the interactions between features in the tabular data. It's not only about the ability to learn these complex high order latent patterns for feature interaction, but as well as the ability to truly parallelize this learning to apply it at scale. And that is where deep learning, the transformer, enables this unlimited parallelization, which, by the way, transformer is a way of avoiding the bottleneck of parallelization, which recurrent neural networks used to have for a very similar purpose of modeling sequences. And it removes this loop, this iterative component of the recurrent neural networks, and transformer is able to do it all in parallel by splitting matrices into pieces and fully parallelize it, which is something which somehow we can do in XGBoost with gradient descent. Gradient descent for XGBoost is highly parallelizable, but the trees themselves it's not that easy to parallelize the tree, because in order to learn the tree, you need to know about the previous splits, and it happens somehow sequentially. So in that from that point of view, in that component, in that dimension, the XGBoost kind of algorithms are less scalable because the parallelization is bounded to certain dimensions. And one more thing is that, well, it's one more extra layer of parallelization, both in terms of scalability and both in terms of learning patterns, because attention, we usually take this approach of multi-head attention, which can look into interrelationships between the data, between the features, in several contexts or towards several unrelated kinds of representative features, and each of them is a separate head. So the representation is even more sophisticated. It is even more nuanced with this multi-head attention. So it's I I'm feeling in my applications of when I practice machine learning that more and more I can find that deep learning transformer is very good and is beating XGBoost for tabular data because of these reasons. It's always been a key optimization of systems. Many times is to think on these two-tier levels. If we want to deal with very uneven data sets, and we want to, for a positive, we need a million negative labels into a data set, and we need to provide that for a single step model, supervised model. Data becomes very unmanageable very easily, and even more, it gets very diluted about the positive instances, or very skewed targets that we want to measure and we want to model. If we do it two-tier, we can think about a way of representing data, learn robust representations and strong latent representations in embeddings about the data, about the structure of our data set. Taking an unsupervised approach, so unrestricted that it is. And that is the first tier, that is the pretraining. And then you move into the supervised side of the problem, and it's just a few samples, a few instances, and you get the problem solved. So it's very efficient in that way. There is an idea about efficiency that I many times think about it, because when people think about they say, okay, we're moving from XGBoost to deep learning because on inference time we have a massive cost of resources. We need a lot of computation and very short latencies. Deep learning, because of infrastructure and parallelization, allows us to perform efficiencies beyond what XGBoost allows to apply in inference. And it's partly true. But I think there is a more subtle way, a more profound way of optimization that is many times, I'd say, overlooked. And it's the idea that you can, for the same amount of performance in accuracy of the model, in deep learning frameworks, you can compact the network, make it small model, more less parameters. So that means less memory and less compute because there are less operations to perform on the inference. And you remove effort and cost from the inference if you put it back into training, because the very same model you can run it for much longer, um, for much longer epochs. You provide more fitting, more computing to fitting the model, maybe increase dropout or tuning the learning rate. The idea is to place more computation into training in order to be able to reduce it and difference time, where sometimes is more bounded to resources and to latencies. Um, Sometimes I think people think about running and applying optimization um, for deep learning in contrast to XGBoost, but I think that many times we are not able to capture the powerful of this optimization of being able to interchange effort and computation between move it from inference into training. So that's important, and that you cannot do it the same with XGBoost, because you can maybe put more interactions, more iterations into in, into XGBoost in training. And what you create is wider and more numerous trees or deeper trees. Depends on the implementation, but many times you end up creating more trees, which eats you alive. And it's a pain when you need to deploy to prod to run in the inference time with simply more trees. And when we mean more interactions, more iterations of training in XGBoost, and that is something that I think many times is lost in the reasons why deep learning is more efficient. Yeah, it's simply, I think the key idea is that transfer learning is so powerful because it's a very smart two-tier system, two-tier solution to approach things in a smarter way and capture this. Even you can recycle these unsupervised modeling outcomes, these unsupervised embeddings, if you like, unsupervised checkpoints for training downstream models into more challenging tasks, or simply if you have several tasks which are common and share some common input data, and they share some patterns, but the outcome is different. If you have different events that you want to predict, you can simply share them by training a common supervised learning, a pretraining, which is shared across different fine tunings. And sometimes you need to fine tune the same thing into different tasks. Um, this unsupervised fine tuning schema is just so powerful, it's so flexible, and applies to that many places that it's. I think if you want to do modern machine learning and you are not thinking of this, maybe you are stuck like almost 10 years ago in the past, and it's simply too powerful. So attention is all you need. It's that is said that many times that it's almost no funny now, but I think transfer learning beating and deprecating fine, but I'd say that transfer learning, pre-training, fine-tuning schemas are deprecating XGBoost-like models. That is a strong statement, and I think that is the best key takeaway, and the best and the thing that takes my attention mostly when I think of from a statistical point of view how to address machine learning problems and how to tackle problems with this approach, which is so powerful that I'm willing to back to working into that again. So hope you enjoyed, and yeah, keep on fine tuning from a good pre-trained starting point.